Welcome to the deep dive. Today, we're exploring this really highly technical 2026 presentation by a researcher who goes by the handle Luck036.
All right, the paper is titled Normal versus Stable Ellipsoid, a Performance Comparison at Every Scale. And it is dense.
Yeah, extremely dense. But our mission today is to decode all this research because, hidden inside all that math is a really surprising truth about optimization algorithms.
Exactly. It's all about how to make these critical algorithms essentially numerically bulletproof, but without sacrificing like a single drop of speed.
Right. Okay, let's unpack this. To really grasp what's at stake for you as a listener, I want you to imagine trying to find the absolute lowest point in this massive, totally fogged-in valley.
Like you can't see more than 2 feet in front of your face.
Yeah, exactly.
Yeah.
It'd be terrifying if you were just wandering around. But you aren't. You have this tool. Imagine a flexible, glowing boundary. We'll call it an ellipsoid.
Which is just a fancy mathematical shape, basically.
Right, like a glowing bubble. Step by step, you use this boundary to shrink your search area. You test the ground, you shift the boundary, you shrink it again, and you just keep doing this over and over.
Narrowing your focus until you are standing at the absolute bottom of that foggy valley.
Yeah. And that shrinking boundary is the whole essence of the ellipsoid method. But in the real world of computing, this process has, well, a hidden enemy.
A very persistent enemy.
Before we get to the brilliant solution in this paper, we need to understand the villain here. What's going wrong when a computer tries to shrink this ellipsoid down in the fog?
So the villain is this phenomenon called numerical drift. And to understand it, you have to realize that a computer doesn't actually draw a physical shape, right?
It's all just numbers in memory.
Exactly. The ellipsoid is maintained purely as a shape matrix. Mathematically, it's represented as a capital P.
Right, I saw that in the paper. P in the set of symmetric positive definite matrices, or SN++.
Yeah, that's the formal notation. And for that ellipsoid to actually exist as a closed, valid shape that can trap a solution, this matrix P has to maintain that strict mathematical property. It has to stay positive definite.
I kept seeing that term everywhere in the source material. Positive definite. Like in plain English, what does that actually mean for our shape?
Think of it as the structural integrity of the bubble. A positive definite matrix guarantees that if you push on the shape from any direction, it pushes back.
Okay, so it stays a convex bubble.
Right, but if the matrix loses that property, the math just completely breaks down. The bubble doesn't deflate, it mathematically turns inside out.
Oh, wow.
Or it flattens into some impossible dimension. The shape just ceases to exist in a way that the algorithm can even use.
So as long as it stays positive definite, we're good.
Yeah.
And with every step in that foggy valley, the algorithm applies what the paper calls a rank 1 update to shrink the ellipsoid.
Yeah, it takes the old matrix, runs some math, and spits out a slightly smaller, shifted matrix.
But computers aren't perfect, right? I mean, they don't have infinite precision.
Exactly. They use floating point numbers. They only have so much memory to store a decimal. So eventually, they just have to round things off.
Which seems harmless enough.
And what's fascinating here is that on a single step, a rounding error is totally invisible. I mean, we are talking about microscopic fractions of a decimal point.
Right, like rounding at the 15th decimal place isn't going to ruin the shape of the ellipsoid.
Not on step 1, no. But you aren't just taking one step. These algorithms take hundreds, thousands, sometimes tens of thousands of steps.
It's like, well, think of it like navigating with a compass that's off by, say, 1/10 of a degree.
That's a great way to look at it.
Right. If you just cross the street, you won't even notice you veered slightly left. But if you try to walk from New York to California with that same broken compass, you'll end up hundreds of miles off course.
Exactly. Those tiny floating point rounding errors accumulate. Over thousands of rank 1 updates, the errors pile up, and eventually matrix P is no longer positive definite.
The structural integrity fails.
It mathematically collapses in on itself, and when that happens, the algorithm just fails. It either crashes outright or, which is actually worse, it silently spits out garbage data disguised as a real solution.
Which is an absolute nightmare. I mean, if you're using this to design an airplane wing or manage an autonomous power grid, you can't have garbage data.
Definitely not.
So since numerical drift can literally destroy the algorithm from the inside out, how do we fix it? And that leads us directly to the 2 contenders that Luck036 discusses in the source material.
Right, we basically have 2 completely different ways to update that shape matrix. First, there's the standard way. The paper calls this the normal approach, or just L.
I mean, Looking at the math, the normal approach is basically a blunt instrument. It just does a direct rank 1 update on P.
Yeah, it takes the current shape, applies the new data, and calculates the new shape all at once.
And it scales at O of n squared, meaning the computing time grows predictably with the size of the problem.
Which is great. It's simple, it's direct. But it comes with a massive warning label. It has absolutely zero stability guarantee.
None at all.
None. If those rounding errors start to pile up, the normal approach doesn't care. It just blindly follows the bad math right off a cliff until the matrix collapses.
Yikes. Okay, so then in the other corner, we have the challenger, the stable approach,
Yeah.
or L-stable, as the research calls it.
This is where the math gets really, really clever. Instead of updating the whole assembled matrix directly and risking that collapse, the stable approach uses an LDL transpose factorization.
Okay, we need to pause and break that down, because LDL factorization sounds incredibly intimidating.
It sounds way worse than it is, I promise. Think of the full matrix P as a complex, fully baked cake.
Okay, cake, I'm with you.
Instead of trying to chemically alter a baked cake every time you take a step, the stable method breaks the matrix down into its core structural components.
Which are the L and the D.
Exactly. The L stands for a lower triangular matrix, and the D stands for a diagonal matrix.
So it's kind of like separating the recipe instructions. The L from the raw ingredients, the D.
That is a perfect analogy. When the algorithm takes a step, it doesn't touch the fully baked cake at all. It updates those base factors directly. It tweaks the recipe and the ingredients.
Wait, I have to push back on this for a second. Factoring a matrix on every single step. Like, I'm not a mathematician, but unpacking and repacking a massive mathematical suitcase every single time we take a step.
It sounds heavy, yeah.
Shouldn't that completely ruin our performance? I mean, doing an LDL factorization on every loop has to absolutely nosedive the processor speed.
It is a completely logical assumption. Honestly, it's exactly what most software engineers assume when they first look at this.
Right, it just seems so inefficient.
But the LDL transpose factorization is uniquely powerful in computer science for one very specific reason. It is square root free.
Meaning the processor doesn't have to calculate any square roots at all.
Which is a massive deal. Calculating a square root is incredibly expensive for a CPU. It just eats up processing cycles. So by avoiding square roots entirely, this specific factorization stays remarkably efficient. But far more importantly, it gives us an ironclad mathematical guarantee.
The stability guarantee.
Yes. Because of the way the D factor, that diagonal matrix, is structured, as long as the numbers running down its diagonal stay strictly greater than 0, the fully assembled matrix is guaranteed to stay positive definite.
Oh, wow. So it physically cannot collapse. The shape will always remain a valid convex bubble.
Guaranteed numerical stability. Even with massive floating point rounding errors, the underlying math forces the shape to stay intact.
That's brilliant. But to my earlier point about the computing cost,
Yeah.
you still have to do all that unpacking.
You're not wrong there. It absolutely involves more complex scalar operations behind the scenes. There is significantly more bookkeeping happening on the processor to manage those separate L and D factors.
So the real question is, does this complex bookkeeping actually slow things down in practice? To answer that, we have to look at how Lux036 actually tested these two methods in the real world. We need to step onto the benchmark battlefield.
And we really need to emphasize how rigorously this was tested. They didn't mess around here.
No, they didn't just run a Python script on a laptop, you know?
Yeah.
The source details this really heavy-duty 2026 testing environment.
Yeah, they threw a 20-core CPU at this.
With AVX2 enabled, meaning the processor was fully optimized to do massive amounts of parallel math. And they compiled it on MSVC 2026 using modern C++ 20.
Orchestrated with Google benchmark version 1.8.3, I believe.
Yep, and they even used a dual build system with both Xmake and CMake, just to guarantee the build environment wasn't introducing any weird bias.
It's some very serious hardware and software orchestration. But, looking at the paper, the most important part wasn't the 20-core processor.
Well,
No, it was the philosophy behind the test. The golden rule of this experiment was verify correctness first, then measure performance.
which is a rule a lot of developers love to ignore, right?
Yeah. Oh, totally. There's this huge obsession with raw speed. But, you don't get a medal for doing the wrong math really fast.
Exactly. So before the timer even started, both algorithms had to produce the exact same optimal solution within a 10 to the power of -6 tolerance.
They had to match out to the millionth of a decimal point.
And they threw a really diverse set of test problems at these algorithms to prove it. They started small, doing these 2D profit optimization problems, both normal and robust variants.
Which only took, what, 80 to 90 iterations?
Yeah, just getting warmed up. Then they scaled up to synthetic random problems, testing from 16 dimensions all the way up to 256 dimensions.
That's a huge jump.
But the ultimate stress test they ran was this thing called FIR filter design, scaling from 32 dimensions up to 64 dimensions.
Yeah, the FIR, or finite impulse response filter problem. If we connect this to the real world, this is a notoriously difficult challenge in digital signal processing.
Like audio engineering.
Exactly. If you've ever put on noise-canceling headphones and just marveled at the silence, or streamed really clear audio over a bad connection, FIR filters make that possible.
Oh, cool.
They mathematically carve out the unwanted frequencies while letting the good ones pass through.
The source explains that the goal of this test case was to minimize stop band attenuation while respecting passband ripple constraints, which sounds incredibly technical.
It is very technical, but conceptually it just means block all the bad background noise completely, but do not distort the good audio even a tiny bit.
But the truly mind-bending part of this specific test case is that it's a convex problem with infinite constraints. How does a computer even solve something with infinite constraints?
Well, because a frequency spectrum isn't just a list of whole numbers, right? It's a continuous wave.
Oh, right, it's analog.
Exactly.
Wow.
When you design a filter, you aren't just checking if it works at exactly 100 hertz and then 101 hertz. You have to account for 100.1 hertz, 100.001 hertz, and literally every infinitesimally small fraction in between.
Which requires an algorithm that can handle immense continuous mathematical pressure without snapping.
It is the absolute perfect torture test for numerical drift.
So they run all these tests, the 2D problems, the 256-dimensional stress tests, the infinite constraint FIR filter designs. What's the result?
Drumroll, please.
All 9 out of 9 test cases passed. The stable version, using that complex LDL factorization, produced identical solutions to the normal version.
Even though it was taking a completely different mathematical path to get there.
Okay, so we know they both arrive at the exact same answer. They both find the bottom of that froggy valley. But what happened to the speed? Did unpacking that mathematical suitcase slow the stable algorithm down?
Here's where it gets really interesting.
Tell me.
The performance was practically identical across the board.
Which defies almost everything we assume about computational overhead.
Yeah.
I mean, when you do more complex math, it should take more time.
It really should. Let's look at the actual numbers from the paper. In the simple TOD tests, the normal method took 96.3 microseconds. And the stable method took 100.4 microseconds.
That is within a 5% noise margin. You literally couldn't blink a fraction of that fast.
Exactly. But you might say, well, that's small scale.
Right. What about the massive 256-dimension problem?
At 256 dimensions, the normal approach took 359.4 milliseconds. The stable approach took 367.2 milliseconds.
That is a mere 2% difference.
And when you look at the scaling chart in the presentation, across all dimensions from 16 up to 256, the per iteration cost scaled perfectly.
The ratio is just completely flat.
Yes, they both scale at exactly O of n squared.
I really struggle to wrap my head around this. I know you said there are no square roots, but the stable method is still doing way more bookkeeping with the L&D factors.
It is.
So how is this parity mathematically possible?
It all comes down to the mechanics of something called flop count, which stands for floating point operations.
Okay, so a measure of the actual arithmetic steps.
Right, how many additions, subtractions, and multiplications the processor is physically taking.
So how many flops does the normal method use?
The normal method spends its operations on a very heavy matrix vector multiplication, followed by a symmetric rank 1 update.
Because it's dealing with that dense, fully assembled matrix.
Exactly. Almost every position in the matrix has a number in it, so the processor has to do a ton of cross-referencing. If you tally up all that math, it totals roughly 2 times n squared flops.
Okay, so the baseline is about 2n squared operations.
Now look at the stable method. It avoids that heavy initial multiplication entirely.
Instead, it does the forward substitution, right?
Forward substitution on the L factor, back substitution on the transpose, and then a specialized LDL rank 1 update.
Which just sounds like way more steps.
It does. But remember what those L and D factors actually are.
The lower triangular and diagonal matrices.
Right. And by definition, a lower triangular matrix and a diagonal matrix are mostly filled with zeros.
Oh, wow. I see where this is going.
When a computer multiplies by 0, it doesn't have to do any real work. It just skips it.
Because the answer is always 0.
Exactly. So even though there are technically more structural steps in the stable method, the matrices involved are so sparse that the processor just skips massive amounts of arithmetic.
That is so elegant.
When you add up the actual math being performed, the total flop count for the stable method also comes out to exactly approximately 2 times n squared flops.
It makes so much sense when you explain it like that. It's almost like, okay, think of two people driving to the exact same destination.
Okay, I like this.
One person takes the main highway, the other person weaves through all these complex, winding back streets. But somehow, because of traffic or whatever, they end up driving the exact same number of miles and they arrive at the exact same millisecond.
That's a perfect analogy. The stable method does more structural setup weaving through the back streets, but the actual updates are so incredibly lightweight because of all those zeros.
The processor just rips right through them.
Exactly. So they arrive at the exact same answer at the exact same millisecond.
This raises an important question, though. Now that we know the stable method provides total numerical safety without any speed penalty,
Yeah.
how do you actually apply this to your own projects?
Right. When would you ever use the normal method if stable is just as fast and guarantees your algorithm won't crash?
Well, the source material is surprisingly objective about this. It doesn't just tell you to throw the normal method in the trash.
No, it has its place.
There are a few very specific scenarios where normal is still recommended. First, for rapid prototyping. If you're just hacking together a quick proof of concept, the normal code is mathematically simpler.
It's much easier for a human to write, read, and debug.
Exactly. It also mentions real-time or embedded systems. If you're coding for a tiny microchip inside, say a smart thermostat, the normal method has slightly simpler vectorization.
Which can sometimes play nicer with heavily constrained low-power hardware.
Right. And finally, extreme high-dimensional problems. If your optimization problem is pushing past 1,000 dimensions, that tiny 2 to 5% overhead in the stable method's bookkeeping might finally start to compound.
It might eventually become measurable, yeah. But outside of those very niche cases,
The verdict for your production deployments is absolute. L-stable is the default.
it has to be. It is highly recommended for long-running optimizations. I mean, if your code needs to iterate 50,000 times, numerical drift isn't just a possibility, it's an inevitability.
The normal method will eventually fall apart.
And the research points out one specific environment where the stable method isn't just recommended, it's absolutely mandatory.
Which is,
Mixed precision environments.
oh wow, that is incredibly relevant today. A lot of modern AI and machine learning hardware relies heavily on mixed precision, right?
Totally. To save memory and process massive data sets faster, modern GPUs constantly switch between standard 32-bit floating point numbers and smaller 16-bit numbers.
But 16-bit numbers have terrible precision. You have way fewer decimal places to work with.
Exactly. The rounding errors happen almost immediately, and they are severe. If you try to use the normal ellipsoid update in a 16-bit environment, the matrix will collapse almost instantly.
Because it just can't handle the aggressive rounding.
Right. But the LDL factorization in the stable method handles that low precision remarkably well. The structural guarantee of that D matrix keeps the shape intact even when the numbers are highly truncated and fuzzy.
So what does this all mean for you as the listener? It basically means L-stable is free insurance.
Which you never get in computer science.
Never. There's always a trade-off. Usually you trade speed for safety or memory for precision. But here you get guaranteed numerical stability, absolute protection against matrix collapse at zero measurable performance cost.
You get all the safety without paying the toll.
It really is a remarkable piece of optimization research. I mean, we started this deep dive looking at a terrifying problem. Numerical drift silently ruining complex optimization algorithms from the inside out.
Then we explored this highly complex LDL factorization method that frankly seemed like it would just bog down any CPU.
But through rigorous benchmarking, from simple 2D shapes all the way up to infinite constraint signal filters, this research proved that elegant mathematics can give you rock-solid stability without sacrificing a single millisecond of speed.
And looking at this elegant mathematics leads to a really profound idea, actually. It's drawn right from the future work section of Lectus36's presentation.
Oh yeah, the author hints at the potential for something called adaptive switching.
Yes, it is a fascinating concept.
Walk us through how that would actually work in practice.
Imagine an algorithm that starts out running the simpler normal method, right? But it's constantly monitoring its own internal health.
Like checking its own pulse.
Exactly. It's watching those floating point errors accumulate in the matrix in real time, and just before the matrix loses its positive definiteness.
Just before the shape collapses and crashes.
Right. The software autonomously detects the danger. And in a fraction of a millisecond, it seamlessly switches its own internal architecture to the stable LDL mode on the fly.
That is just incredible.
It heals itself, stabilizes the calculation, and finishes the job without a human ever intervening and without the calculation ever slowing down.
It completely changes how we think about software. I mean, if algorithms can mathematically self-diagnose and heal their own foundational structure mid-calculation, it moves code from being fragile to being almost, I don't know, biologically resilient.
It really does. And it makes
Yeah.
you wonder what other software systems in our lives could be revolutionized by this kind of autonomous, self-healing mathematics.
Like, could we build operating systems that repair their own memory leaks in real time?
Or autonomous vehicles that mathematically stabilize their own failing sensor data before a human driver even realizes there was a glitch.
It opens up a future where algorithms aren't just fast, they're unbreakable.
Completely unbreakable.
So the next time you find yourself dropped into a massive, completely fogged-in valley, trying to find your way to the bottom, you don't have to worry about your equipment failing on you.
The boundary won't collapse.
The math holds up. You just have to take the next step. Thanks for joining us on this deep dive.